Hey, AP Chemistry. I'm going to warn you, this is probably going to be a bit of a long video, but that's okay. This unit is going to get split into two parts. One is a little bit more on the atomic structure. We'll dive into Bohr and quantum mechanics. And then the second half will be looking at the trends in the periodic table. And you need both to go together. So you might want to take some notes. Obviously, this is going to be on homework assignments, tests, etc. And I hope it helps you. The first thing we need to talk about are waves and something called the electromagnetic spectrum, electromagnetic radiation. Hopefully there's still a poster in my room. Right now it's on the front counter of the EM spectrum. You can look it up in your book. You can look it up online. But it consists of the following: gamma rays, X-rays, UV, ultraviolet rays, visible light, infrared, microwave, and radio waves. All electromagnetic waves move at the same speed, which is the speed of light, 3 times 10 to the 8th meters per second. AP Chemistry in your textbook are a little bit more specific, 2.998, but typically in a physics classroom, we just say 3 times 10 to the 8th. All electromagnetic waves have wave-like properties. And if you can't picture a wave, picture dropping a stone on water and the water just ripples. Gives you an idea of a wave. There are different properties arising from different wavelengths, and we'll get into that more later on. On the next slide, I'm going to break it down into the different components of a wave, but the wavelength must always be measured in meters. Now, when you're dealing with chemistry, typically they give us nanometers, so you're going to have to be able to convert to meters. Not that big of a deal. There's something called frequency. That's how many waves there are in, say, 1 second or in 10 seconds in a time frame. That can be measured two ways, either in hertz or per second, or s to the negative 1. For our calculations, the s to the negative 1 works the best. It helps you calculate out and get the right units. And one of the equations we're going to use is this. C is the speed of light, and it equals the wavelength times the frequency. Well, if you think about it, meters times 1 over seconds gets you meters per second. Remember, units are your friend. Let's take a real quick look at this diagram and point out a few things about waves. From the top is called the crest, the bottom is called the trough. From crest to crest or trough to trough, or honestly the same point on two different waves, that distance is the wavelength. The amplitude is just from the middle to the top or the middle to the bottom. Or you can do from top to bottom and divide it in half. That's your amplitude, and that's how big the wave is. The other thing you need to know is that frequency, I think we've already talked about that. Frequency is just how many waves pass through an area in a given period of time. And don't forget, all waves travel at the speed of light. As we get into Bohr's model and quantum mechanics, we need to talk about quantized energy and photons. The wave model of light does not explain a few things. It doesn't explain the emission of light from hot objects. We call that black body radiation. It does not explain the emission of electrons from metal surfaces when light shines on it, the photoelectric effect. And it does not explain the emission of light from electronically excited gas atoms, the emission spectrum. So, what's going on? When an object is hot, it emits light. And if you know anything about stars, red hot is actually cooler than yellow or white. You might want to take astronomy and learn about that. Well, in the late 1800s, physicists were trying to explain the relationship between temperature and the intensity or wavelength of the emitted radiation. Gosh darn it, the laws of physics just didn't account for it. Well, in the 1900s, Max Planck came along, and he assumed that energy could be released or absorbed, but only in discrete amounts, some minimum size. And he used the term quantum to explain this fixed amount. And like most good physicists, Max Planck has an equation. It's E equals hf. E is energy, h is Planck's constant, and right there, 6.626 times 10 to the negative 24th joules times seconds, and V is the frequency. And if you remember that frequency is 1 divided by S, well, joules times S divided by S will get you joules. So energy is going to be in joules. But according to the theory, matter can emit and absorb energy only in whole number multiples. And I'm going to give you an analogy here in just a minute. In other words, energy must be quantized. And for his work in 1918, he did win the Nobel Prize in Physics. How can you picture quantized energy? Well, think about when you walk upstairs. You can only step on an individual stair. You can't step in between the stairs. There's nothing there. So every time you climb a step, your potential energy increases in a quantized way. It changes by the same amount. Well, unless somebody doesn't know how to build stairs and your stairs are completely uneven. But let's go with a good builder here. Well, why don't we notice this in our everyday life? That's because the gain or loss of a single quantum of energy is just too small. And we also need to understand that light behaves both like a wave and like a particle. And this is what we call the dual wave particle nature of light. Bohr used Planck's and Einstein's ideas to explain line spectrum of hydrogen. See, radiant energy can emit a single wavelength of light, such as that from a laser. So take a look at the picture. A continuous spectrum is going to show a rainbow. Emission lines show you what colors are emitted. In this particular case, if you look closely, there are 4 different colors or 4 wavelengths that are emitted. All the other colors are absorbed. Well, most radiation sources produce radiation containing many different wavelengths. We call that polychromatic. A laser might be monochromatic because it only shows you red light. A spectrum is produced when radiation from sources are separated into their component wavelengths. White light separates into all the colors of the rainbow. Black is the absence of light. But not all radiation sources produce all the colors. Instead, you often get a spectrum, and these spectrums can help us identify certain elements. So Bohr knew that there were these quantized amounts of energy, and he assumed that the electrons moved in circular orbits around the nucleus at set distances, at set energies. However, if this were really the case, the electron moving in a circle would continually lose energy and spiral into the nucleus, right? Positive, negative attract. But that doesn't happen. So what did Bohr do? Well, he simply declared that the laws of physics were inadequate. They just don't apply here. Really? That must be pretty arrogant to assume that the laws of physics don't work. While I might pick on Bohr, he did get quite a few things correct. So let's take a look at his postulates. Whether they're correct or not, let's just look at what he came up with. And what evidence does he have for it? Well, he said that there were only orbits of certain radii corresponding to certain energy levels that were permitted for the electron in a hydrogen atom. By the way, everything he did pertained to hydrogen, and the unfortunateness is that that didn't really apply to a lot of other elements. He said that an electron is permitted to orbit in what's called an allowed energy state. It didn't radiate energy. It doesn't spiral into the nucleus. Again, the laws of physics just don't apply here. And he said that energy is either emitted or absorbed by the electron from one energy state to the next. There is a diagram in your book, and by the way, there are PowerPoints, not videos, but PowerPoints that go with some of your corresponding assignments in this chapter. Take a look at those because they point out these figures you want to look at. But basically what this diagram shows is here's the nucleus and here's the first principal energy level, n equals 1. And it takes a lot of energy to go from here to here. But then from N1 to N2, it's like this. And every subsequent energy level you go, it gets smaller and smaller. So it doesn't take as much energy to go from, say, the 5th orbit to the 6th as much as it does to go from the nucleus to 1. So make sure you point that out and take a look at that. So what evidence did he have? He actually calculated energies corresponding to the allowed orbits for the electron and hydrogen, and it fits the Rydberg equation. From this equation comes the principal quantum number n. We'll talk about that more later. Each value of n corresponds to an orbit. The orbit closest to the nucleus is n equals 1, the next one is 2, and so on. And the closer to the nucleus, we call that the ground state. Higher energy states are what we call excited states. So when all the electrons are where we think they should be, we call that the ground state. Let me explain this a little bit further. This is the picture from the textbook. So down at the bottom is n equals 1. So we assume that the nucleus is below that. look at how much energy it takes to go from 1 to 2. It's a huge jump. Then 2 to 3 is a little bit smaller, 3 to 4 is even smaller, and so on and so forth. Well, when an electron is separated from the nucleus, it is called the reference or zero energy. His third postulate said that if electrons absorb energies from a photon, it's going to jump up by that much. Same as if it falls, it's going to give off that much radiant energy. So if the change in energy is positive, we say that it's jumped up to a higher orbit. If the change in energy is negative, we say that it has fallen to a lower orbit. The electron transitions from one allowed state to another involves a photon. Electrons just don't move on their own. Something needs to give them energy, which we will look at in a POGL. The energy of the photon must equal the difference in energy between the two states. If you want it to jump between 2 and 3, you need to give it that much energy. And again, if the change in energy is positive, it means that the photon is absorbed, which causes it to jump up. If it's negative, the photon is emitted and it falls down. So let's sum up Bohr. What did he get right? Well, he said that electrons exist only in certain discrete energy levels, which are described by quantum numbers. That is correct. Energy is involved in transitioning an electron from one level to another. Again, correct. What did he not get right, or maybe not quite right? Well, he was able to explain the line spectrum for hydrogen, but it doesn't apply in any other atom. He said that he wasn't able to explain why the negatively charged electron did not fall into the nucleus. He just assumed that the laws of physics did not work. And he described the electron as a particle. He left off the fact that electrons can also behave like waves. So along comes somebody named Louis de Broglie. I looked that up. It looks like Broglie, but it's actually like Broy. Anyway, he wanted to know if radiant energy could behave as a stream of particles or photons. Could matter behave as a wave? Not light, not electrons, matter. He proposed that the electrons move around the nucleus like a wave. They have wavelengths which depend upon mass and velocity. This is the equation he came up with. Wavelength is equal to Planck's constant divided by momentum, mass times velocity. This could actually be applied to all matter, except larger objects like a golf ball have wavelengths so tiny that you wouldn't observe them. So this led to the uncertainty principle. Werner Heisenberg proposed that the dual nature of matter, that it behaves like a wave and a particle, places a limitation on how precisely we can both locate and talk about the momentum at any given moment in time at a subatomic level. We call this the uncertainty principle. In other words, we cannot say about an electron both its momentum, usually we say its velocity, and where it is at the same time. We can tell you where it is, we can tell you its velocity, but we cannot say both things at the same time. Well, after some fancy math, one can show the uncertainty of the position of an electron in the order of magnitude greater than that of the atom. Well, what does that mean? We have no clue where it is. In fact, the more you get into the quantum mechanic theory, it's really all about probability. It's very ugly math, a lot of calculus and whatnot. And we have electron densities. We have regions where we're pretty sure there's an electron, but we can't say exactly for sure where. Researchers do not even try anymore to find simultaneously both the location and the momentum of an electron. They've just accepted it. They've moved on. Then came Schrödinger and his wave equation. It involved a lot of calculus, but it incorporated both the wave and particle-like behavior of electrons. It led to wave functions, which basically just says that there's probability of where we're going to find the electron. We call this electron density or a probability density. And this is where that whole electron cloud or electron orbital came from. And this is why we use dots to represent electrons, because we're not really sure where it is. But the darker or the more shaded or the more dots means a higher probability of finding electrons in that area. We know now that electrons do not orbit the nucleus like planets around the sun, like Bohr thought. They're actually found in these things called orbitals. And there's 4 kinds of orbitals. The top row is your s orbital. It's spherical. Then the second row are the p orbitals. They look kind of like dumbbells. And then as you get into the d and the f's, they look quite different. Very different, in fact. And again, all of this goes back to the math and the probability of where we think we find the electrons. So let's talk about each of the quantum numbers in turn. If you have not been taking notes up to this point, you probably want to start because you're going to need this information for your homework assignment. The first one we're going to discuss is the principal quantum number, and they use a lowercase n to represent this. I know n can equal mole. It is what it is. This one actually indicates the size of the orbital. You will always see this as a positive integer 1, 2, 3, 4, 5, 6, or 7. As n increases, it means that you're getting farther and farther from the nucleus. Do you remember electron configurations 1s2, 2s2, 2p6, and so on? That number in front of the s, p, f, or d, that's your principal quantum number, your principal, your letter n. There's some vocabulary we need to discuss that gets kind of confusing. The principal quantum number is often called the shell. You're in the fourth shell. You're in the fourth quantum number. The subshell refers to all those orbitals that have the number 3 or 4 in front of them. So if we're in the principal quantum number 3, where do we see 3? 3s, 3p, and 3d. We can also talk about how many orbitals there are. Well, there's 1s, there's 3 p's, and there's 5 d's. So when you add up 1 plus 3 plus 5, you get 9. Hey, 3 squared is 9. Let's see if that keeps holding. Let's do another example. I'm going to skip down a few bullets here. Principal quantum number 4. Well, you have 4s, 4p, 4d, and 4f. So you get 1, 3, 5, and 7. When you add those up, you get 16. Hey, 4 squared is 16. So when you're looking for the total number of orbitals, those shapes on the slide before, for a principal quantum number, take your principal energy level, square it, and you'll get the number of orbitals. Now remember, each orbital can hold 2 electrons. So if there's a total of 16 orbitals, it can hold 32 electrons. Go back to principal quantum number 3. There are only 9 orbitals, which means it can only hold a total of 18. The next quantum number is called the angular momentum, and it is they use a lowercase cursive L. That's what that squiggly thing is. Here's how you find it. You take the principal quantum number and subtract 1, and then it's all the integers between 0 and that value. So if we have the principal quantum number 4, then your value for the angular momentum are 0, 1, and 2, and 3. I can't subtract. It's never the same value as n, ever. Well, the angular momentum actually describes or defines the shape of the orbital. If you have 0, that means you have an s. If you have 1, you have a p, 2, you have a d, 3, you have an f. So think about the principal quantum number 4. 0 is less than or equal to n minus 1. So 0 is less than or equal to 3. Well, 0 would be s, p, d, and f. Don't we have all those with a 4? Don't we get 4s? Don't we get 4p? Don't we have 4d and 4f? Kind of cool, huh? The next quantum number is the magnetic quantum number, and this is m subscript little l. And it has integral values, so no fractions or anything, from negative L to plus L, including 0. This describes the orientation of the orbital in space. So let's say we have quantum number n equals 3. Well, L is going to be 0, 1, and 2. 0 goes with S, 1 goes with P, and 2 goes with D. And don't we have 3S, 3P, and 3D? We do. So what is M sub L? Those values are for L anywhere from the negative all the way to the positive. So because 2 is the greatest number, we go from negative 2, negative 1, 0, plus 1, and plus 2. And this just gives you that orientation of where we find them in space. And if you go back a few slides or go look it up or look in your book, you can see that all these orbitals are arranged differently spatially around the axes. Obviously, S is just a sphere. But when you've got the P, One's in line with the x-axis, one's in line with the y-axis, and one's in line with the z-axis, which is coming out of the page. And then when you get into the D's and F's, you start getting into some really weird looking stuff. I don't even want to talk about it. It's kind of complicated. But that's what we're talking about with this quantum number. The last quantum number is the spin, and this is m subscript s. Kind of hard to see there. But when two electrons are in the same orbital, they have opposite spin. Well, they don't actually spin, but they behave like they do. And so we represent that as a positive or a negative 1/2. And you're going to see in a moment that when we do orbital notations, we do an up arrow and a down arrow to show that they're spinning oppositely. Two electrons can share the same quantum numbers for n, l, and m sub l, but they will always have a different spin. We call this the Pauli exclusion principle. So you can have two electrons that share n equals 4, l equals 3, m sub l equals 0, but where they're going to differ is on the spin. Again, this is the Pauli exclusion principle. Let's take a little bit of a deeper look at each of these orbitals. And now some of this information is not in your book. I actually pulled it from one of the graduate classes I took in chemistry. Believe it or not, I always thought S stood for spherical because it's a sphere, but it actually means sharp. It is spherical. It's around the nucleus. There's only one s orbital per energy level, 1s, 2s, 3s, and so on. The orbital that is really, really close to the nucleus is actually close even within the nucleus. And when you do that, you get this sphere. Just remember that as n increases, the spheres stay spherical, but they become larger. And so the electron density becomes diffuse or more spread out. The 3p orbitals look kind of like dumbbells. You've got kind of those balloons on either side with the nucleus in between. And the orbitals simply differ in their spatial orientation along the x-axis, y-axis, and z-axis. By the way, each of those balloons are actually called lobes. The p orbitals do increase in size as we go down the energy levels. So the 2p is much smaller than, say, the 7p. Just don't forget that each of these can hold 2 electrons, so the p orbitals can hold a total of 6 electrons. Oh, and by the way, p stands for principal. I don't know why. That's what it stands for. I'm not going to talk a whole lot about the d orbitals because they're not that important to AP chemistry. Just know that d means diffuse, and they're found kind of in some odd shapes. I told you can take a look at them. I mean, most of them look like 4-leaf clovers. One looks like a double-sided pacifier with like a donut and 2 dumbbells, and they're just kind of strange. But again, this is where the math claims we're probably going to find electrons, somewhere in this spatial orientation. All I'm going to say about F is that they're pretty ugly. These are mathematical constructs derived from the wave equation that, again, give us the probability of where we're going to find the electrons. Very odd shapes, very weird looking. Remember, each one can hold 2 for a total of 14 electrons. And I might say this again later on, but maybe not. I can't recall for sure if it's in the PowerPoint. Use the periodic table that is in your book or the one that I give you. Here's why. When you pull those 2 rows at the bottom out, not all resources pull out 14 elements. They'll pull out 15, and they don't all pull them out starting with the correct element. Your textbook and any resource that I have given you is correct. Use those when looking at electron configurations. Just very quickly, I know you saw this last year. I just want to touch on it again, but recall that the 1s is closest to the nucleus. The 7s, the 60, the 5f are farthest from the nucleus. Just notice how they're arranged. A lot of students want to put the 3d in between the 3s and the 3p. That's not where they fit. We'll review this as we get more into electron configurations. But this is actually the order in which the orbitals go. The energies of the d and f levels do vary by occupancy. And in AP chemistry, we don't have to get into all of the exceptions and all the weird things, and there's a lot of them. Just hold on to this picture. We're going to come back and use it. in regular chemistry, you were taught how to do electron configurations, 1s2, 2s2, 2p6, and so on. There is something also called an orbital notation, and that's where we use the arrows. So 1s can hold 2 electrons. So we show an up arrow and a down arrow. By the way, you always list the up before the down, just letting you know that. So if you look down at neon, 2s has 2 electrons, an up arrow and a down arrow. And then all of the p orbitals should be filled, up, down, up, down, up, down. If you go and look at oxygen, notice that you've got only one of those p orbitals has 2 electrons, up and down, and then up and up. Nitrogen, up, up, up. So what's important about this is called the Aufbau principle. It's German for building up. The ground state is where no electrons are excited. They're all found where we think they should be. So when you do electron configurations, you need to go one orbital at a time, like you were taught in regular chemistry, and we'll review this before you move on to the next orbital. More rules. So why is the electron configuration in such a particular way? The 1s2, the 2s2, the 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. Why do we do that? Well, Hund's rule states that for all degenerate orbitals, what does that mean? Orbitals of the same subshell. So let's think about all of the 3p. There are 3 different 3p's. Remember, one's oriented along the x, one's along the y, one's along the z. All of those have the same energy. Even though they're spatially oriented differently, they all have the same energy. So for those orbitals, the lowest energy is attained when the number of electrons have the same spin, when that's maximized. What does that mean? This is probably most easily explained by looking at the picture. Here's the correct way to do nitrogen. The 1s has an up and a down arrow because 1s holds 2 electrons. 2s has 2 electrons, up, down. Nitrogen only has 3 in the p. You would put 1 in each orbital. Each one has the same spin. Now, what's incorrect? Well, they put 2 electrons in one of the p orbitals and left one of the p orbitals blank. That's not going to happen. Electrons repel. They don't want to be near each other. They want to be separated. And in fact, when we get into periodic trends, you're going to notice some weird things happening when you go from nitrogen to oxygen. And that's because oxygen has 1 more electron than nitrogen. We have to double up one of those p orbitals. And when we do that, the electrons repel and spread out a little bit more, which makes the atom a little bit bigger, and it actually makes it a little bit easier to take an electron away from oxygen than nitrogen. So when you're doing the orbital notations and you're putting the arrows in, you have to put 1 in each box before you can double up. And they're always going to be up arrows. So if we were filling a 3D block, you would put 1 in each of the 5Ds before you double up. And they would all be up arrows. So the orbital notation has arrows. The electron configurations don't. You learned this last year. We will review this very briefly in a quick homework assignment. The normal electron configuration, 1s2, 2s2, 2p6, and so on. Condensed or shortcut or noble gas formation, what it does is it takes all of the rows before the row that you're in. So for the example I give, aluminum, everything before row 3 is shown with the noble gas at the end of row 2. So neon. And it has to be in brackets, not parentheses. 3s2, 3p1. It's kind of nice. It's faster. It's shorter. It lets you focus on the outer electrons only because, as you're going to see in the next PowerPoint, the inner electrons, yeah, they're important, but as far as behavior, they're not. If you do the condensed configuration for all of column 1, you're going to notice that all of them are number S1. 4s1, 5s1, 6s1. And this is why they behave the same. They all have the same number of outer electrons. I do want you to recall that starting in row 4, you have a D block, and that D block is 1 less than the row. So if you're in row 4, it's actually 3D, 1 less. If you think about, you have to have a C to get a degree in college. D is 1 off from getting that C. And then the F block is also weird. Remember, those 2 rows at the bottom of the periodic table actually belong in rows 6 and 7. Well, if you have to get a C to pass and you get an F, you are 2 below that C, 2. So in the 6th row, we have the 4F, and in the 7th row, we have the 5F. So don't forget that when you're doing your electron configurations. I know this was long, but you made it. Let's just go over a couple of, did you notice? Did you notice the relationship between how many electrons fit in a block and how many columns are in each block? The S block can hold 2. The S block has 2 columns. The P block can hold 6. There are 6 columns, and so on. Did you notice that if you add up all of the exponents on an electron configuration, you get the total number of electrons for that element? There are many exceptions to writing out electron configurations, but the AP board does not expect you to remember those. To be honest with you, if you ever need to, they're really not that hard. There's a lot of patterns that show up. So if you go on and take a higher level chemistry class or a graduate degree in chemistry, you'll have to learn them, but I promise you they're not that awful. When looking at the electron configuration, which part of that is the valence electrons? For this, we're only going to count the electrons in the highest principal quantum number, which would be your S and your P's. We ignore the D's and F's. So if I give you krypton, 5s2, 4d10, 5p3, how many valence electrons are there? Focus on the S's and the P's. 2 plus 3 is 5. This element has 5 valence electrons and fits in column 15. Now, go tackle all your homework assignments. Go back, rewatch this if you need to.